In this chapter, we are looking at sequences and series. In this particular lesson, we are going to take a look at geometric sequences.
So now we're going to look at geometric sequences like we just introduced there. And a geometric sequence is one in which each term is produced by multiplying, and there's the key word here, this is the differentiating feature here. We're multiplying the previous term by a constant, okay? And that constant stays the same throughout the entire sequence while you're building it. Just like in an arithmetic sequence where you add the same thing over and over and over again. Here, we're multiplying by the same factor over and over again. So here's an example. 3, 6, 12, 24, 48, blah, blah, blah. Okay, now, like I say right here, I think it's pretty clear that the factor you're multiplying by here is 2. Okay, now, but think about how you got that. Okay, let's just zoom in a little bit here. Sometimes it's really easy to see the math, and then we make this intuitive jump. But if you just back up and think, well, how did I know that? Okay, there's some math that comes out of that as well here. And so notice in this case here that the way we got that we were multiplying by 2 here is that we took 6 divided it by 3. 12 divided by 6, or 24 divided by 12, and so on. Okay, we're doing division here. Now, notice we're not going 3 divided by 6, not 6 divided by 12. It's 6 divided by 3, 12 divided by 6. We're taking a term further along the sequence and dividing it by the one right in front of it, which is actually what this little rule here is saying. If you take the nth term and divide it by the n minus 1th term. So think of it like this. If n is equal to 5, this becomes the 5th term over the 4th term. If n is 4, this is the 4th term over the n minus 1, 4 minus 1, the 3rd term. And this gives us just a way of calculating it. If we just, again, think about the process that we're going through to get that value. Now, because we're finding this by division, we call this the constant ratio. Okay, the value that the variable that we're going to use is r, okay, constant ratio. Now, let's just take a quick look, we'll zoom out a little bit here, at how that above sequence was created. And we're going to show you if we can get a sense of how a general geometric sequence is modeled here. So the first term was 3. And you know what, we might even use a again to refer to that first term, just because it's a convenient variable to use here. So to get the second term, I multiplied it by 2. Okay, to get the next term, I multiplied it by 2 again, so that means 2 squared. To get the next term, I multiplied by 2, I'll zoom in a little bit, I multiplied by 2 again, which creates 2 cubed. Now, notice that when I look for the 4th term, I'm cubing the common ratio there, okay? When I'm looking for the 3rd term, I was squaring it. The 2nd term, I had it to the power of 1 here. Notice that the exponent on the common ratio is always 1 less than the term number I'm looking for. And this gives us a general term for that particular sequence, right here. 3 times 2 to the n minus 1. Now, please remember to put brackets around that, because then it looks like 30. If you don't, it's 32 to the n minus 1. And that's not what we're trying to get at here. You've got to have brackets around that to separate out the terms here. So this is then, whoops, wrong way, whoa. Okay, this is then the general term for this geometric sequence here. Now, in general, what we can do is we can write it like this. Okay, for any particular geometric sequence, the general term is going to be t sub n is equal to a times r to the n minus 1. A is the first term, r is the common ratio. Okay, now, before we go on and take a look at a couple other things here, just a little note here. Whoops. R could be negative. Okay, so if r was negative, let's go back to that previous section there. The previous example there, r could have been negative. So I could have gone 3 to negative 6. And if I multiplied this by negative 2, I'd get positive 12. And if I multiply that by negative 2, I get negative 24, and then positive 48, and so on. So what we're seeing here is if r is negative, then what happens here is the signs on the terms alternate, which is why we call this an alternating sequence. Okay, just a little bit of vocabulary there, something to be aware of. Now, before we get into start doing examples here, something that we want to take a quick look at, in just a quick comparison here, I want to compare the plots between an arithmetic sequence and a geometric sequence. Okay, so This first one here, and I know for one reason or another, the grid plotted in a really, really light pink, and I'm not sure why. But here's my graph here. I've highlighted the dots here that are the values of an arithmetic sequence. Notice that an arithmetic sequence here is linear. Okay? It just goes up by a constant value here. Basically, the slope is the same. Okay? I go up by whatever the d value is, the common difference is, but I'm always going over 1. Okay? So this is why this is linear here. However, for a geometric function here, what happens here is our plot actually does this. Okay? And this is what we would call exponential. Okay? Growth can be quite slow for quite a while, and then all of a sudden it shoots up and it grows very, very, very fast. Okay? So these are the two different graphs related to these two types of sequences that you've looked at. This is an arithmetic sequence, and this is a geometric sequence. The domain in both cases here is going to be an element of the naturals, okay, because we're still using n to count the terms in the sequence, starting at term 1 and then going up to whatever term we want. But it's always first term, second term, third term. There's no fractions. There's no negative values there. We don't even include 0. Okay, there's no 0 with term. Okay. So the domain here is naturals. This is what an arithmetic an arithmetic sequence could be dropping, by the way, just like an exponential or a geometric sequence could be dropping as well. But the point is, it's going to have this nice curve to it. An arithmetic sequence is going to have a straight line graph to it.
Find the common ratio, the general term, and the eighth term for the sequence 1, 3, 9, 27, and so on.
Okay, well, to find the common ratio for this sequence, really what we got to do here is just divide consecutive terms here. It doesn't really matter which pair you take here, but I think it's going to be pretty clear that even if you take just the first two, 3 divided by 1 is 3. So the common ratio here is 3. Okay, 9 divided by 3, 27 divided by 9, they're all 3. The first term is going to be 1. I love that. So now the general term is going to be Tn is going to equal A. Well, I'm not going to write 1 because I'm going to be multiplying here in a second. 1's not going to do anything. I mean, if I really need to, I suppose I can. Okay, but this will be 1 times 3 to the n minus 1. Okay, or just 3 to the n minus 1. So there's the general term. To find the eighth term, I just substitute in an 8 for the n. So this becomes 3 to the 8 minus 1, or 3 to the 7. Now this is just calculator work. And I get 2,187. So there's my r, there's my general term, there's my eighth term.
Find the common ratio, the general term, and the eighth term for the sequence 5, negative 25, 125, and so on.
So to find the r in this particular sequence here, it's just a matter of dividing two consecutive terms. But notice, importantly, that we're going to get an alternating sequence here because notice we're going from positive to negative to positive. Negative 25 divided by 5 will be negative 5. The negative is important here. The a value here is clearly 5. And so therefore I can write my general term as 5 times negative 5 to the n minus 1. Okay, now I might be tempted to try to multiply these together because I've got a sort of a common base here, but there's a negative there, and unless I deal with that negative appropriately, I'm going to end up creating the wrong general term for the sequence. So you know what, you're probably better off just leaving it like this. If it wasn't for the negative there, I could multiply those together, okay? And just by adding exponents to them. But because this is a negative, and the negative is important as the base, okay, to that exponent there, I'm just going to leave it here. So there we go. So there's the general term here. Now, to find the eighth term, that will be 5 times negative 5 to the 8 minus 1. And again, that's just calculator work. So 5 times negative 5 to the power of 7. I can do that part in my head. And this is large, negative 390,625. Okay. Shouldn't come as a surprise though, because these things tend to grow really, really quite quickly here. Exponential functions, if you think about the graph that we looked at just a couple minutes ago, it swoops up really, really quickly.
Find the common ratio, the general term, and the eighth term for the sequence 128, 64, 32, and so on.
So to find the R value here, I just take two consecutive terms and divide here. And it doesn't matter which ones we do. Kind of lazy here, so I'm going to take the smaller of the numbers here. 32 divided by 64. Yeah, it turns out that's a half. Okay, and the same thing would be true if I divided 64 by 128. Okay, don't always be trying to avoid the fraction. Don't think, well, I'll divide this way, because no, you can't. You can't divide 128 by 64. You're moving in the wrong direction. Okay, so if fractions come up, all that means is the values are getting smaller. That's okay. A is 128, and so that means, that means that our general term could be written as 128 times 1/2 to the n minus 1. Now, this one could be simplified. Okay, unlike the previous one, because there's no negative here, and it turns out both of these numbers are powers of 2, I can do a little bit of simplifying here. Now, depending on who your teacher is, it'll depend on whether you're going to be required to do this or not. But notice, and this is something you would have done in previous course even, 128 would be 2 to the 7. 1/2 would be 2 to the negative 1. Now this is still being taken to the power of n to the power of n minus 1. Now I just have to apply order of operations. First of all, I do the exponent. Okay, and so this is going to be equivalent to, okay, we're still talking about the general term here. I'll deal with this 2 to the 7 in just a second here. I've got 2 to the negative 1 to the n minus 1. Well, that is going to end up being 2 to the 1 minus n. Okay, the negative 1 distributes through, begins negative n plus 1, and I just change the order. Now, add those two together, okay, because I'm multiplying powers, I add the exponents. So this becomes 2 to the, well, what's 7 plus 1 minus n? 8 minus n. Okay, so there is a simplified form of the general term. I couldn't do that in the previous question because of the negative in there. And well, granted, I probably could have, but I would have had to separate out a couple of numbers there, and I wouldn't have been happy. This is a much more straightforward way of doing that. Now, to find the eighth term, I'm just going to use my simplified form. That's going to be 2 to the 8 minus 8. Well, 8 minus 8 is 0, and 2 to the 0 is 1. So my eighth term here is 1.
Find the common ratio, the general term, and the eighth term for the sequence 4, 4 root 3, 12, and so on.
So to find the R value for this one, again, just a simple matter of division here. But I'll write this one out a little bit. I'm going to take that second term, 4 root 3, and divide it by the first term, 4. You should see really quickly that the 4's cancel, and you're left with root 3. So in spite of the fact that that's a little ugly there, that radical, I got it fairly quickly. It was just a nice little cancellation there. My A is going to be 4, the first term. So therefore, my general term will be 4 times root 3 to the n minus 1. Okay? So now, to find the eighth term, okay, this is going to be 4 times root 3 to the 7, sorry, not to the 7 minus 1, I'm anticipating the answer there, to the 8 minus 1, or to the 7. So this will be, the eighth term will be 4 times root 3 to the 7. Now let's just think about this. Root 3 to the 7. Every pair of factors in there is going to get me a 3. Right? Because root 3 times root 3 will be 3. So if I've got 7 of them, I've got 3 different pairs. Basically what I'm asking you to do is to simplify this right here, this radical, because I can move that 7 inside here. And what I'm going to get here, what I can pull out of that will be a 3 cubed times the square root of 3. Okay, so 3 cubed is going to be 27, and 27 times 4, this will be 108 root 3. Okay, I just want you to kind of think about the math that you've done previous to this. You would have worked with radicals before. We're just going to simplify this root 3 to the 7. Okay, that's all we're doing.
Given the sequence 64, 128, 256, out to 16,384, find the number of terms and the position of the term 2048.
So to answer this question, we really need to find the general term for this particular sequence right here. Now it's easy to tell that the first term is 64. It's given to us right there. And then the R value, well, let's just take a quick look here. 128 divided by 64, well, it's going to be 2. So I can tell that the general form for this expression will be 64 times 2 to the n minus 1. Now, that could possibly be enough to figure out the rest of the question here. However, I probably want to simplify this a little bit more here, because notice that 64 is a power of 2. 64 is going to be 2 to the 6. And this is going to be 2 to the n minus 1. I can do a little bit of simplifying here, because now that I've got two powers with the same base here, I can just add exponents. So this becomes 2 to the n, let's just think, negative 1, and 6 is going to be n plus 5. So Tn is going to be 2 to the n plus 5. Now that makes it very, very simple for me to take a look at the following, the other questions here. It says determine the number of terms in the sequence, okay? Well, here's my last term, 16,384. Whatever the n value is for that term, that will be the number of terms in the sequence. So 16,384 is going to equal 2 to the n plus 5. Now, there are a few ways that I could do this. Okay, I can start to rip this thing apart and so on and so forth, and break that down into powers of 2. Or what I can do, and this is actually what I want to do here, I'll show you how to do this on your calculator. Go to your y equals, and we'll enter 2 to the power of x plus 5. This is our general term here in simplified form. Now I'm not going to graph it. What I'm going to do is I'm going to go to my table of values. Okay, second graph right here to get to my table of values. Now what I'm going to do, this is just now a list of all the terms in the sequence, and I'm going to go down and find out where 16,384 is, and it tells me that occurs where x is equal to 9. Oh, so what that means is there are 9 terms. And when it asks me to determine the position of the 2048, I can go back up to here and just look for 2048. Well, it turns out that's the 6th term. So 2048 is term 6. Just an easy way to use your calculator. There's really no other way to deal with this at this point other than reducing this down to powers of 2, getting the value over here written as a power of 2, or essentially using your calculator to do it. You'll see in Math 30, when you start to look at logarithms, how there's another algebraic way of approaching that.
Find the missing terms in the following sequence: blank, blank, 45, blank, blank, negative 1,215, blank.
Okay, for this question right here, we're trying to fill in the blanks in this particular sequence here, and I know this is a geometric sequence. Okay, I know I can count this out. I know that this is my 3rd term, and this is my 6th term. Now, I had a way at one point of doing this that I thought was fairly good. You kind of counted things out and blah, blah, blah. But I actually watched a student do this once, and they had an interesting way of approaching this, and I think I'm going to show you guys this right here. The 6th term is negative 1,215, okay? Now think about what that is. My 6th term, remember that the general term is AR to the n minus 1. Now I don't know A or R, okay? If I knew those, then I'd be laughing here. But I don't. I do, however, know that the 6th term, when n is 6, I get negative 1215 when n is 6. So this is AR. If n is 6, n minus 1 is going to be 5. Now, at the same time, I know that the 3rd term, when n is 3, the 3rd term is 45. So when n is 3, 3 minus 1, 2. When n is 3, I get this right here. Now, one of the things that I can do And you would have seen this before when you were solving systems of equations. What we're going to do here is something very, very similar. Except what I'm going to do now, instead of adding and subtracting these equations, I'm going to divide. So I'm going to take negative 1215, and I'm going to divide by 45. And we'll get negative 27. On this side right here, when I divide, notice that my a's cancel, which is great. That's what I wanted. I'm eliminating in a variable here, but I'm eliminating it this way, this time doing division. R to the fifth divided by r squared is r cubed. I just subtract the exponents. Well, now I'm down to something really straightforward. What's the cube root of negative 27? Well, you can go to your calculator to get that. The answer is r is equal to negative 3. That is really all I needed to be able to answer this question. If r is equal to negative 3, well, that means to go forward along the sequence, I multiply by negative 3. To go backwards, I divide by negative 3. So that's going to give me negative 15. And then divide that by negative 3 again. It's going to get me positive 5. Now, multiply 45 by negative 3 to go forward. It's going to be negative 135 times negative 3 is positive 405. Now, I'm going to multiply by negative 3 just to make sure that I get that. Times negative 3, and yep, there's my negative 1215. And I'll multiply that by negative 3 to get 3,645. That's what I needed to do. This idea of dividing to get rid of the a value there is really quite clever, and it makes use of some algebra that you really should be comfortable with.
Find the geometric mean of the numbers 3 and 48.
So what this means here is that there's a sequence that we're forming, and there's a single value between 3 and 48. So really what this is it's actually sort of similar to the previous question. There's a sequence here, there is a missing value. I want to know what that term is. When I say geometric mean, if this is a geometric sequence, what number belongs right there? Well, if this is the entire sequence right now, and this is this little finite sequence, I know that my starting value is 3. The thing is, I don't know what r is, but I do know that the third value is 48. And that actually gives me a couple bits of information. I know the term, I also know the end value. So if Tn is equal to AR to the n minus 1, let's take a look at putting all this information together in here. I know that the third term is 48. My A value is 3. I don't know what R is yet, but I know that this has got to be to the 3 minus 1. Well, let's do a little bit of simplifying. Let's divide by 3. We'll get 16 is equal to R. 3 minus 1 is 2, R squared. Now, here is the trick. When you take the square root of 16, I don't know whether you meant the positive or the negative value for the 4, because it could have been either. Which means that the actual number that we're looking for here, so 3 comma blank comma 48, whoops, sorry, you can't see that. I could have multiplied by either positive or negative 4 to go from one term to the next here. So this means that this could have been plus or minus 12 as a geometric mean. And you have to look for both of those, or else you've gotten it wrong. You've missed part of the answer.
Given that the third term of a sequence is 12, and the seventh term is 192, find the first term and the 12th term.
So to answer this question here, we're going to really take advantage of the fact that we know that the general form of a geometric sequence should look like this. So when I give you, for example, and I'm going to start with the term that's further down the sequence here, okay? Because when I come up with my R value, I always divide the further along term by an earlier term. I'm going to start with what is being told me right here. I know that 192 is the seventh term, but this tells me that n is 7. I don't know A, I don't know R, but I know that's going to be to the 7 minus 1. The third term being 12, same thing. I know that the term is 12. And that's telling me that the n is 3. Now, just like I did in the previous question, I'm going to divide. So 192 divided by 12 is 16. Now, I know that the question was asking me for A, but when I divide right here, A's are going to cancel. All that means is that I'm going to need to go back. Once I've figured out what R is, I'm going to have to go back and find out what A is. Now, so the a's cancel. 7 minus 1 is 6. 3 minus 1 is 2. And then when I do the division, I'm going to go 6 minus 2. So this is going to be r to the 4. Okay, now, when I take the fourth root of 16, this could be plus or minus 2 is equal to r. Okay, so there's a couple options here. Now let's go back. Let's take, for example, our t3 is equal to 12. Okay, so t3 is equal to 12. What that means is 12 is going to equal a times, now here's the thing, I don't know if this is plus or minus 2 times 3 minus 1. Now, 3 minus 1 is 2. Whether you're dealing with plus or minus 2, the answer here is going to be 4. So what that means is it doesn't matter. It means that my first term, when you think about the pattern of alternating signs here, that means my first term is going to be one of those positive terms here. So divide, and I'm going to get a is equal to 3. Okay, just positive 3. Good. Now, to find the 12th term, I'm just going to use now what I know. Okay, the 12th term will be 3 times, now it could be positive or minus 2 to the 12 minus 1. Okay, let's go to the calculator here. Now, if 12 minus 1 is going to be 11, when you take a positive value to the 11, it'll be positive. But if you take a negative value to the 11th power, it will stay negative because it's odd. So 2 to the 11 is 2048. So this is going to be the same as 3 times either positive or negative 2048. And if I multiply by 3, that means my answer here could be positive or negative 6,144. Now again, I have to be prepared to give both answers if I want to get full marks for that.
Given that the terms x minus 8, 2x minus 10, and 4x plus 10 form a geometric sequence, find the value of x.
Okay, I know that this kind of question can be really intimidating for a lot of people here because of all the algebra involved. And you're looking at 3 terms all given as binomials here, okay? But think about what is constant about a sequence, okay? Now, granted, the first term, when you're building the terms of a sequence, you're always going back to the same first term here, but eventually you move away from that first term. But what are you doing that's constant all the way through? Well, with an arithmetic sequence, you're always adding the same amount. With a geometric sequence, you're always multiplying by the same amount here, which means to go from one term to this term, I multiplied by some value, and that's going to be the exact same thing that I multiply when I go from here to here. So the trick to answering this problem is to understand that the ratios are going to stay the same. And this is why you're given 3 terms. Okay, so just remember, note that r, the common ratio, would be t2 divided by t1, which would be the same as t3 divided by t2. Now, in this context, that means I can take 2x minus 10 over x minus 8, and that's going to be the same as 4x plus 10 over 2x minus 10. Okay, that ratio has to be the same. This proportion has to be true. Okay, this is r, and so is this. Okay, now step back from the fact that this is a geometric sequence and just look at it as a rational expression. Okay, what we're going to do here is I'm going to want to solve this, but I'm going to multiply. Basically, I'm going to cross multiply here. Okay, so I'm going to get 2x minus 10 times 2x minus 10, which will be 4x squared. Okay, what is that going to be? Minus 20, minus 20. So minus 40x plus 100. And I'm going to multiply x minus 8 times 4x plus 10. So that's going to be 4x squared. What am I going to get here? It's going to be 10x minus 32. So minus 22x minus 80. Now what's nice about that is that the 4x squared is going to cancel here. So I'll bring the 40 over, bring the 80 over. Okay, so the 4x squareds cancel. I've got a negative 40x here. I've got a negative 22x here. I'm just going to add 40 to both sides just so that I get a positive value on the right-hand side here. And what's that going to be? It's going to be 18x. I will add the 80 over to get 180, and when I divide, I'm going to get x is equal to, whoops, sorry, you can't see that. I'm sorry, I'm working off the side of the screen there. Okay, so just to reiterate what happened here, the 4x squared terms are going to cancel. I added 40x to this side to get rid of it, so I add 40x, and then I'm going to add 80, I'm going to add 80, which got me 180 equals 18x, and then when I divide by 18, I get that x is equal to 10. But what makes this thing work right here, what makes this question happen is this ratio right here, okay? These ratios here are always the same. It's a constant ratio here.
If x plus 3 and x squared plus x minus 6 are two consecutive terms of a geometric sequence, find the common ratio and the next term.
Okay, so in this question right here, notice that I'm going from a linear first term to a quadratic second term. Okay, I think I'm going to factor that second term. T1 was equal to x plus 3. T2 is equal to x squared plus x minus 6. Well, what does that equal here? Well, x squared plus x minus 6 is going to be x plus 3 times x minus 2. So there's my first term multiplied by x minus 2. Well, this is what I multiplied by. Therefore, r must equal x minus 2. So now the third term is going to be the second term multiplied by r. Well, my second term was x squared plus x minus 6. And my r was x minus 2. Okay, well, you might not like it, but you're going to have to do some distribution here. This is just pretty straightforward polynomial multiplication. It'll be x cubed minus 2x squared plus x squared minus 2x minus 6x plus 12. And so just grouping together like terms, x cubed minus x squared minus 8x plus 12. That's our third term.
The number of fish in a lake decreases by 5% each year. In January 2015, there were 2,500 fish in the lake. How many will there be in January 2020?
Okay, this question right here is very likely going to cause a lot of problems, and people won't even notice what's going on typically with a question like this until you get to the end and realize that your answer is incorrect. There are two things happening in this problem that tend to cause a bit of grief here. So first of all, we're going to take a look at this is, sorry, Tn is equal to AR to the n minus 1. We're going to take a look at our geometric sequence equation here and kind of relate it back to the pieces here. First of all, the number of fish in a lake decreased by 5%. Now, when we talk about a percentage, we're going to be doing some multiplication here. So obviously we're referring back to the R value. But what is the R value? Well, in this case here, R is not 5%. It's not 0.05. Because in the formula here, whenever we use it in the formula, we're always referring to what's left behind. This is what's being taken away. So R, okay, if you are losing 5%, you are left with 95%. So R is actually going to be 0.95. Okay, in the equation, you're always addressing what you've been left with, not what you're taking away. Okay, so there's the first big issue there. A lot of people will just immediately jump in and not think about it. 0.05, move on. Nope. It should be pretty clear that A is going to be 2,500. Now, when we take a quick look at this, though, timing, the time becomes an issue. Which term is it in January of 2020? Well, you think here, well, between 2020 and 2015, that's just 5. You know, you subtract them, you get 5 here. But you're not actually thinking carefully enough about this here. Let's just take a quick look at the timeline. Here's 2015, 2016, 2017, 2018, 2019, 2020. Now, I don't suggest that you do this for every single question that you write on a timeline, but to see it once, I think will help you get a sense of what's going on here. Remember that just a brief reading of this, it makes sense that the first term would be 2,500. Okay, that's the number of fish January of 2015. But what that does is that makes this your first term. So that makes this your second term, third term, fourth term, fifth term. This is actually your sixth term. We are looking for the sixth term to get to 2020. See, what happens when you take 2020 and subtract 2015, you're basically eliminating 2015, and you've got those five right there. When the number 5 that we get by that subtraction are these 5 numbers, not including the 2015. So you have to add one additional value to get a sense of how many are in that group here. Okay, so finding n is the other issue here. So now I know that I'm looking for the sixth term. This will be 2,500 times 0.95 to the 6 minus 1. And now I just go to my calculator. 2,500 times 0.95 to the power of, well, what's essentially going to be 5 here. And I get 1934.5. Now that's rounded to 0.5. And I have heard from a few people that it's, actually, sorry. I shouldn't have done it like that. I should have written it like this. This is approximately 1934 point, let's say 452 and so on. You can, I've heard arguments that you can round this either up or down when you're talking about fish like this. But my advice to you is round to the nearest whole. So it's approximately 1,934. Just if you round to the nearest whole, you should be fine in every case.
A sample of bacteria doubles every 3 hours. What is the initial count of bacteria cells if after 18 hours there are 24,768 cells?
Okay, here's another question that really requires you to pay careful attention to the terms that you're looking at here. Now, a sample of bacteria doubles every 3 hours. Okay, well, I think it's pretty clear. Doubling means multiplying by 2. Okay, it doubles every 3 hours. So what is the initial count of bacteria? So I'm looking for A. If after 18 hours there were 24,768 cells. Okay, now I gotta get my head wrapped around kind of what's happening here. This doubles every 3 hours, and I'm waiting till after 18 hours. So what's happened here is, sorry, I don't want to identify n right now because there's an issue with that. Think of it like this. Let's take a quick look at that number line again, like we did in the previous question. Okay, so here's time is equal to 0, and then here's 3 hours, 6 hours, 9 hours, 12 hours, 15 hours, and I'm off the screen here, and then 18 hours, okay? So here's our clock. We're trying to figure out how many bacteria were here right now initially. Now watch this, ignoring everything else here. After 3 hours makes the number of bacteria at the 3 hour mark term 2. We start here where time is equal to 0, so this is term 1. This is term 2, term 3, term 4, term 5, term 6, term 7. See, this is where people are going to get thrown off by this, because you're going to see that this is broken down into chunks of 3 hours. And 18 divides by 3 nicely. 18 divided by 3 is 6. But 6 is not the term number for that last term. It's the 7th term. The reason for the mix-up here is because when time is equal to 0, that is our first term. Time is 0, but it's term 1. And so after the first 3 hour mark, that's term 2. So basically our counting has shifted over 1. So what I know back here now is that n has got to be equal to 7. So what I'm going to do is I'm going to fit in my values now. I know that I get, for my 7th term, I've got 24,768 cells. I don't know what the initial value is. I know that I'm doubling it, and this will be to the 7 minus 1. Okay, well, 7 minus 1 is obviously 6, and 2 to the 6 is 64. So now if I take 24,768 divided by 64, I get that there was a beginning, okay, there were 300, therefore there was 387 bacteria to begin with. Whoops, can't see that. There you go.
During the first weekend of a movie, 15,000 people watched. Only 52% of the previous attendance watched on each subsequent weekend. The theater stops the movie when the attendance drops below 360. How many weekends did the movie play at the theater?
Okay, so in this question here, they're not really hiding any of the information here. So what's going to happen here is we're going to have to be a little bit clever in how we solve it. But the information here is not being hidden. The A value here is 15,000. Okay, we started off with 15,000 people. Only 52% of the previous attendance watched, so that means that each week we are maintaining 52%. So our R value here is 0.52. What we're being asked for here is we're being told at some point right here, if the nth term goes to 360, that's when we shut it down. So the question is, what is n here? Where does that occur? Now, finding n can be rather difficult. So I'm going to show you what we're going to do here. We're going to set up our equation though. So 15,000 is going to equal to, I'm sorry. I did that backwards. 360, sorry, is going to equal 15,000 times 0.52, whoops, you're not seeing that, to the n minus 1. So what we're going to be looking for here is n. Now, well, okay, there are a couple of different ways that we could go about doing this. What I would probably do is this. I would go to the calculator and plug this in. Actually, sorry, what I would probably do first is actually, you know what? I'm second guessing myself. I'm going to do it like this. What I'm going to do is I'm going to split this up left side versus right side here. The left side of the equation is 360. The right side is going to be 15,000. And then I'm going to multiply that by 0.52 to the exponent of x minus 1. There was another way that we could do this. I could have divided both sides by that 15,000, but that would be dealing with some really, really small numbers, some decimal numbers that would be hard to kind of look at. I am not actually going to graph this. What I'm going to do is I'm going to go into my table of values. So second graph. And now what I'm going to do is I'm going to slide down here. Okay, 360 is my goal, okay? And I'm going to go down here until, and here's the problem right here. First week, now, okay, when n is equal to 0, that's the 0th term. That actually doesn't count for anything. It's the first weekend here was 15,000, and it is in the 7th that number there drops below 360, okay? So we did this just by using the table of values. Okay, so the theater stops. The theater stops the movie when the attendance drops below 360. So in the 7th weekend, okay, we get a number below, and so after that it stops here. So the 7th weekend was the last. There you go. You'll see in math, your next level of mathematics, when you take a look at logarithms, how you might solve this in a different way.
A clever child convinced his mother to only give him a penny for his allowance, but she would have to double it each week. How much would he receive on the 30th week?
Okay, let's take a quick look at this one. This would be a great idea if you could convince your mom to do this for you here. So the child here is only going to get a penny for the first week. So that's 0.01, obviously, okay, with the way we work with our money here. And we're going to double it, which means our R is going to be 2. And then we're interested in knowing how much money would occur on the 30th week. Okay, so after getting your allowance for 30 weeks here. Okay, so this is a pretty easy one to set up for here. We're looking for the 30th term. It's going to be 0.01 times 2 to the 30 minus 1. Okay, so 0.01 times 2 to the 29. Let's just go to our calculator here. Oops, we'll quit out of that. So, whoops, 0.01 times 2 to the power of 29. Ooh, look at that. Okay, let's make sure we put our commas in the right spot here. That is, okay, 5,368,709.12 for your 30th week. That's before like the year isn't even over, and look how much money mom has to give you. That's a great deal for that kid. Not so good for mom.
A ball is dropped from a height of 70 meters. After each bounce, it rises to 80% of its previous height. What is the height after the 7th bounce? After which bounce does it reach a height of approximately 1.1 meters?
Okay, this question right here shows up a lot. We show it every year. It features prominently between lessons here. Okay, this is going to be a question we're going to come back to over the next couple of lessons as well. So it's something that you really need to be prepared for here. Now, there are a couple of different ways to approach this. The issue is all about where you start counting the terms in this sequence. You just need to be consistent with that. If you get that down pat, you should be fine regardless of how you approach this. So a ball is dropped from a height of 70 meters. Now, I think most of us, no, not everybody, but most of us are going to interpret that as being your A value. That's your starting term here. So let's just draw this over here. So it starts, there's the ball, and it's going to bounce. It starts at 70 meters up. Okay? And then it's going to start to bounce here. And every time it bounces, it bounced to 80% the previous height. So my R value is going to be 0.8. Okay? So here's my first bounce. Okay, goes up, down. Here's my second bounce. Okay, and then so on, third bounce, and so on. Now, the reason why I'm writing this out here and taking time with this is going to keep going forever here. You have to be really, really careful about this, because the question is going to now ask, after which bounce does it reach a height of approximately 1.1 meters? Okay. After which bounce? But the problem is, how does this relate to the terms? I just identified that this was term 1. And if this height right here is term 1, well, okay, the bounce, when it hits the ground, isn't the term. Okay, the terms are counted on either side of the bounces. So here's the next height that I get to. This is T2. The second term happens after the first bounce. Bounces aren't terms. Okay? This right here, after the second bounce, that's my third term. So I hope you get the connection here. You need to be really clear as to what their terms are in this scenario here. So now what we're going to do here is, I don't know when that occurs, okay? I'm looking for the height that's approximately 1.1. So I'm going to build my general term here. So again, Tn is equal to AR to the n minus 1. So now I plug in what I know. 1.1 is going to be 70 times 0.8 to the n minus 1. So now I'm looking up here. Like I did with a previous question, I'm going to go back to my y equals. I'm going to enter in 1.1 for the left-hand side of the equation. Then I'm going to enter in 70 times 0.8 to the power of x minus 1. Okay, and I'm going to now go to my table of values, and now I'm going to start to look and see at what point, which term are these approximately equal here. Now, the question is pretty clear with this. This is not like that time problem where you always have to round up. I just want to know at what point is this number here the closest to that 1.1? So I go down here. We're at 11 already down here. Keep going. Okay, oh, we're getting there. Okay, so here we go. So look at this. 1.26 or 1 point. Which of those is closer to 1.1? Well, this one is. This one here is 0.16 away from 1.1. This one is the closest here. So at approximately the 20th term, okay? So when n is 20 is the closest, okay, is the closest Tn is to 1.1 meters. Now let's just think about this. When does that occur then? The 20th term occurs, now watch this, the second term occurs after the first bounce. The third term occurs after the second bounce. So the 20th term occurs after the 19th bounce. So this is after the 19th bounce. That's what we're looking for. You just got to be really careful about where you start this the function here. Some people will think that what they'll do here is they'll let this be term 1. And they'll just think that the first height is the height after the first bounce. And there's no problem with that. But what that means is you now have to figure out what your first term is, because this is no longer your first term. This is your first term. So it doesn't matter. You either do a little bit of kind of clever thinking at front or a little bit of clever thinking at the end here. Either way works out great. Oops, I almost forgot to answer the first question here, which was what is the height after the 7th bounce? Now I've already set this up here as to how we might do that. Okay, for the 7th bounce, okay, after look at this, after the second term is after the second bounce is my third term. So if I want after the 7th bounce, okay, after the 7th bounce, what I want is n is equal to 8. I want the 8th term. So to do that, okay, the 8th term is going to be 70 times 0.8 to the 8 minus 1. Okay, I'm just going to go to my calculator. Now, the expectation here is not that this is going to be the difficult part of this problem. The expectation, quite honestly, is that you're going to have troubles putting together which term number it is you're talking about. But at this point here, you're just going to plug this in, and the answer here is it's approximately 14.7 meters when I enter that in my calculator.